Here on 2.4, we're working with the idea of complex numbers. So this is really coming from our dealing with quadratics and quadratic formula. This is ultimately dealing with that imaginary unit I, or as some of us have already kind of shown this year, the square root of -1. Now, with this introduction of complex numbers, that means we're actually allowed to have negatives in the square root, but also in turn that means we're allowed to have imaginary zeros or complex zeros, which we're going to be seeing by the end of this unit. Well, a few things to do before we kind of go into the operations of such a complex numbers. First thing being, first off, we have I, right, which is the square root of -1. We want to look at a few other values. I squared, I cubed, and I to the fourth. If I look at I squared, which is going to be a pretty common thing we see, well, if we square this side, we get I squared. What happens if we take the square of the square root of -1? We just get the inside, which is -1. Now, if we were to multiply this I squared by another I, thus making it I cubed, but we need to do that on both sides, then ultimately we're going to have negative I on the left, sorry, on the right, which gives us the negative of the square root of 1. Sorry, negative of the square root of -1. And to get I to the fourth, we can look at this I squared that we already had, right? If we multiply the left and right by I squared, multiply the left, we get I to the fourth. Multiply the right, we get negative I squared, but that's just negative of -1, thus giving us a +1. So these are four of our main values. We have I, which is the square root of -1. I squared is just -1. I to the third is the negative of the square root of -1. Then I to the fourth brings us kind of back full circle to I equals 1. From there, if we were to do a fifth power, sixth or seventh, it's going to kind of rinse and repeat as one of these iterations. But those four are the main ones to kind of get down. Now, with imaginary units, this idea of I, comes the standard form of a complex number. And where we do that double bar R for real numbers, we have the C with a line through it for complex numbers that I'll be using. And the standard form of a complex number is typically in the form Z equals A plus BI, where A and B, so A comma B, these are elements of the real numbers. So if we have the standard form of a complex number, it's really some real piece, some complex imaginary piece, then you bring them together for that standard form. Now, one last little thing before we go into some of the operations. We only have a quality of two different complex numbers if the real piece of one is equal to the real piece of the other. So A, equals C. And also, we need to have the imaginary piece of one match the imaginary piece of the other. If we have that happen, then we know we have equality between those two complex numbers. But for the most part, we're going to be dealing with putting things into our standard form, the A plus BI, which we're going to see on these next 8 problems of dealing with some of our operations. Now, the first 4 are dealing with either addition, subtraction. And the nice thing about addition, subtraction of complex numbers is I'm going to be using the phrase component-wise, we add them. And here's what I mean by that. If we add or subtract 2 complex numbers, we add the real pieces together, so 7 plus 5, and then we add the imaginary pieces together. So plus 3 plus -4, so 3 minus 4, I. And then we just simplify. 7 plus 5, we get 12. There's our real piece. 3 minus 4, we get -1. But -1 times anything is just going to negate what that is. So we get -1I, or just negative I left over. Now moving on to number 2, a little bit of subtraction. How does that work? Well, again, we're going to be dealing with the real pieces first, but now we're dealing with subtraction, so it's 3 minus 5 for the real piece, and then it's 4 minus -3, so 4 plus 3 I, and we're always keeping the I onto the right for us. 4 plus 3 I. And then just like here for number 1, we're just going to simplify that. 3 minus 5, -2, 4 plus 3 plus 7 I. So the next two, no different. We just have multiple of them, right? But the same concept applies where we're going to add only our real components, add the imaginary components, and then simplify that together for the complex number. So give it a little pause, try out number 3 and 4. It is one more number added in there, but that same process. So give it a pause, give it a try, we'll work it out in a sec. All right, hopefully you paused it. Number 3, even though we start with just 2i, which is really saying we have 0 for the real piece, I'm still going to start by grouping up all my real values. So I have -3 here, and I'm subtracting 3 more. Now I'm going to add now all 3 of my complex pieces I have, or imaginary. So I have 2 here, 2i here, minus 4i here, and then minus negative, so plus 3i over there. And again, you notice I'm just adding kind of those coefficients of the I, and then I'm tagging that I on the end. You can think of it almost like you factored it off. Oh, just like above, we're simplifying. -3 minus 3, we get -6. 2 minus 4, we get -2. We add 3, you get +1, or just I. Again, anytime you have just an I or a negative I, or -1i, you can just put the I itself. Now, moving on to the number 4, again, I'm going to do my real pieces to the left, imaginary to the right. So I have 5 plus 3 minus 8. That's my real piece. And then I'm going to have my imaginary piece. I already know that's where the I is going to go. I have -3 plus 5, and then -2. And so we go to number 4, we go to simplify. 5 and 3, what does that give us? 8, right? But then you subtract 8, so all this cancels. So we lose that real piece. And then we go to the imaginary piece. So you have -3, we add 5, that's 2, but then -2. We also lose all of the complex piece as well. And when it comes to complex numbers, we don't need to write 0 plus 0i. We can simply just write 0. So a 0 in complex, same thing as a 0 in our real numbers. Well, that's addition subtraction. Nice and easy, just component-wise. Add the real, add the imaginary, throw it together. When it comes to multiplication, we can kind of think of foiling or distribution as our go-to. So for the first, right here, a number 5, we see we have a complex number inside parentheses and a -5 outside, kind of like our vertical stretch and shrink. And the nice thing about this is we're just going to be multiplying it like we would do distribution. So I have -5 times 3, that's -15. And then I have -5 times -2, so that's +10, but we need to remember to bring that I along with it. So if we do have a problem where it's just one constant out front of a complex number, you could think of it as scaling each of those by that factor. Now, more common to what we're going to see are things like number 6. Number 6, we have 2 completely different complex numbers being multiplied. And as I said, you want to think about foiling when you go about this. So number 6, we're going to work out the whole thing. We'll kind of speed it up for 7 and 8. So for 6, we got 2 times 3, which is 6. We have 2 times 3i, which is 6i. We have negative 4i times 3, so the negative 4 times 3 is the negative 12. Make sure you bring the I with it. And now it's this last piece that's going to be notorious for kind of tripping us up. So we have the negative 4 times our 3. So you would typically go, oh, negative 12. But it's not negative 12i because we have to also multiply the i's together. So we get negative 12i squared. Now this looks a lot like something quadratic, right? With an x squared, x's. So we have like terms we can add up. But we also have a nice little substitution we can make. Back at the beginning, we said I squared was if you squared this, right? So it's just negative 1. So when we resimplify this, this really isn't a minus 12i squared. It's a negative 12 times a negative 1, but that gives us plus 12. So this turns into just positive 12. Well, now like before, it's just a problem of addition subtraction. I have my 6 and 12, which is 18. 6i, but I lose 12 of them, so minus 6i. So a big thing to pay attention to is when we run into these problems over here. When your I, that imaginary piece, starts to gain powers, we always want to replace it with what that value is. So that it's just the real piece and then the one imaginary piece. So keeping that in mind, I want you guys to give 7 and 8 a try and see what you guys get for that. So give it a pause. Same thing, we're going to FOIL. For number 8, you can kind of think of it the same way. We're just going to FOIL and see what you guys get. So give it a pause. Take a second to do it. All right. Hopefully you did it. We'll work through these a little bit quicker. So for number 7, we have 4 times 4. We get 16. We have 4 times negative 5i, so negative 20i. But then we have a positive 20i right here. So you get negative 20i. That other middle term is a positive 20i. If you haven't noticed, those will nice cancel. And then again, it's this weird end piece. 5 times negative 5, negative 25. Kind of hold that aside for a second. But then it's an I squared. So negative 25I squared. We want to make sure we handle that I squared. Well, just like over there we saw I squared, it's just negative 1. So really this is as if we multiplied negative 25 times negative 1 or plus 25. And then after that, again, it becomes an addition subtraction problem. Combine your real pieces, the 16 and the 25. We get 41. Nope, we don't get 41. Yes, we do. And then what happens in the middle? Well, we already kind of made comment of it, right? We have a negative 20i and a positive 20i. Those are just going to cancel out, leaving us with something that is strictly a real number with no imaginary piece, which is also totally fine. And we may want to pay attention to this example 7. Something about its form is going to come back to help us out. But lastly, we'll do number 8. For number 8, you could rewrite it. So 4 plus 2i times 4 plus 2i. Or we can use what we already know. If we have any binomial squared of this form, we square the first. So there's our 16. We multiply these together, and then we double it, right? So that's 8i, but then doubled is plus 16i. Then lastly, we need to square this last little bit. Now, when we square this, the 2 is squared, and the I is squared. So again, it comes into this problem when that last little bit of that I squared kind of being that tougher piece to deal with. But 2 squared, we know that. That's just 4. And the I squared is now going to make it negative. So this piece really turns into a minus 4. And like before, just a distant subtraction. 16 minus 4 gives us 12. And then this imaginary piece of the plus 16 is untouched. So again, when it comes to operations, we'll kind of see what happens with division coming up. But addition, subtraction, you're just doing component-wise. Add the real, add the imaginary. And multiplication, you're either treating it like distribution or as if you were foiling it. And that big thing to look out for is the I squared, and making sure we sub that in with that negative I. So in order to deal with division of complex numbers, we first have to deal with something called a complex conjugate. So ultimately what that is given some complex number, its complex conjugate has the exact same real value, but then the opposite imaginary value. And ultimately, this is a tool we're going to use, as we'll see kind of on the next page, in fact, of how we can divide with complex numbers. But first, we just want to deal with how can we find the conjugate and what happens if we multiply a complex number by its own conjugate. And that's what we have at the bottom of that first page. So I'm going to put both of these in parentheses because ultimately we're going to multiply. And when it comes to finding the conjugate, we only have to look at the imaginary piece. So the real piece is going to stay the exact same, 3. Instead of plus 6i, we're going to be subtracting 6i. And I'm going to do number 10 at the same time where I'm going to find the conjugate, and then we'll multiply them separately. So for number 10, maybe even you give it a try, right? Give it a quick pause. Did you get the conjugate? Not too bad, right? The real piece stays the same. Now, it's not that it's always negative. Like here, it's just that we're taking the opposite. So if it was negative, we multiply it by its opposite, which is positive. Now, this might look somewhat familiar, maybe to number 7 that we did. And we'll kind of relate back to that in a sec. So doing number 9, remember multiplying is just kind of like foiling. 3 times 3, we get 9. We're going to get negative 18i, positive 18i. We'll get some canceling right there. And then we got to deal with this I squared business again. So 6 times negative 6 is negative 36. And then it's going to be an I squared. Well, as we saw in the last one, those middle terms are going to cancel out for us, which is nice. And now we have this I squared. Remember, I is the square root of negative 1, and I squared, well, if we square that, it's just negative 1. So it's more like multiplying the negative 36 by negative 1. So it's minus 36 times negative 1. That just turns it into addition, and we get 45. Now, if you look back to number 7 and look at the other problems we did with multiplication so far, for the most part, we kept having real pieces, imaginary pieces for all those. However, specifically, when we multiplied it by ultimately its conjugate, that's what we did ultimately on number 7. To take a little look, you can see that one of those is the conjugate of the other, that the imaginary piece in the middle cancels, and also by squaring that I term, we removed the imaginary piece completely. So if we multiply something by its conjugate, it's as if we removed the imaginary piece, or we removed that square root of negative 1 from the entire problem. So very similar. Number 10, give it a pause, give it a quick try. Doing the exact same thing we just did at number 9. We already found the conjugate. Now just give it a quick multiply. All right. Hopefully it didn't take too long. Now, instead of foiling it, I'm going to show us a little trick for when we're multiplying conjugates. Let's look back at number 9. Ultimately, at number 9, we end up with 9 plus 36, right? Well, 9 is just the 3, the real piece squared, and 36 is just the 6, the imaginary piece squared, and then we add them together to get that 45. Now we can do that same exact thing over here in number 10. We could take the real piece, that 2, it gets squared. We add the imaginary piece, the 5, it gets squared. And that's 4 plus 25, that just gives us 29. So two things that are really nice with complex conjugates. One, they're always going to give us just a real value when we multiply conjugates by one another. And also, if we are doing it, we can kind of skip a lot of work, right? We don't have to even FOIL. We're just going to square those two values and add them together. So that is what a complex conjugate is and kind of how it affects stuff. And now we're going to look at how we can use it in this world of either division or simplifying some things. So for starters, with 11 and 12, we're going to do a little bit of division. And I'm going to help you out with whenever we're writing things in standard form, right? Let me erase this for us real fast. Standard form was that A plus BI. So we had a complete piece that was real, complete piece that was imaginary. It didn't have this blending happening like we're seeing on 11 and 12. So we need to be able to break that up. But the only way to break up a fraction like this is if the denominator were to be one value, right? Then we could have 2 over that value, and we could have the imaginary piece over that value. And that's exactly what we're going to do, but with conjugates. Another reason we're doing this, I is equal to the square root of -1. We might remember this from Algebra 2. We like to rationalize the denominator, which means we don't like square roots in the denominator. So this is another way for us to remove square roots or remove the I from the denominator. So to do that, we have to multiply the top and bottom to change the denominator, just like with normal fractions, right? But instead of multiplying it by itself, we want to multiply it by its conjugate, because we know it gives us just one value, and that's going to help us out a ton. So we're going to multiply top and bottom by the conjugate of the denominator, 2 plus I, and also the top 2 plus I. Now, the bottom is really nice for us, right? We just did that. We have that over here. The bottom is going to be 2 squared plus 1 squared, which is just 5. And now it's really just the top that we got to work with. And again, that 5 I got by just multiplying those two denominators. Well, for the numerator, we have 2 times 2, which is 4. We have 2i and 2i, so we get plus 4i. And then lastly, we have I times I, right? Because we're going to be FOILing this. And I times I is just I squared. But we know what I squared is, right? If we square I, we get just -1. So this becomes a -1, 4 minus 1 plus 4i all over 5. And here's where we start to get that thing into standard form for us. 4 minus 1 is 3. So we have 3 over 5. And then we can have the complex or the imaginary piece separate, right? That's going to be the 4 over 5. But remember, this has the I, so we want to make sure we include that I in there for the imaginary piece. So when it comes with dividing complex numbers, it's not that we really divide as much as we rationalize the denominator, aka multiply top and bottom by our complex conjugates. That gets rid of the I in the denominator and lets us split things up in the numerator to get it into standard form. Now, give number 12 a shot. We're doing the exact same thing we did here. But remember, we're not looking at the conjugate of the top value. We're looking at the conjugate of the denominator. So give that a quick pause and a quick try. All right, we'll do it together now. Number 12, multiply top and bottom by the conjugate of the denominator. 3 minus 2i, 3 minus 2i. It's just convenient that these were the same value. It doesn't have to be the case. Well, just like here, denominator is easy, right? 3 squared plus 2 squared. Well, it's 9 plus 4. That's going to be over 13 for us. And again, that denominator is just from what I did over here with multiplying conjugates. I'm just relying on the fact that if I know multiplying conjugates, you could square the two values and add them. Now we got the top. We got 3 times 3, 9, minus 6i, minus 6i, minus 12i. And then we have negative 2 times negative 2, so plus 4, but I squared. Again, I squared is negative 1, so it's really a 9 minus 4 minus the 12i over 13. And then lastly, just like we did on this first one, 9 minus 4 is 5, so there's our real piece, 5 over 13. Then we already have our imaginary piece already simplified. It's minus 12 over 13, but we got to make sure we include that I, so we know that this is the imaginary piece. So if we're dealing with either dividing or trying to rationalize the denominator, we're always going to be relying on these conjugates. Now for numbers 13, 14, and 15, we're relying on something a little bit different. We're kind of relying back on this original definition of I. So I'm going to make some room over here for us, get rid of number 10. So looking at number 13, square root of negatives. Typically we can't do it, right? However, we know what the square root of, not negative 15, but we know what the square root of negative 1 is. So we're going to take both of these radicals and break them apart. So we'll have square root of 15 times the square root of negative 1. If you multiply those, you get back to this. And you have the square root of 3 times the square root of negative 1. Again, if you multiply these together, you end up back at this. Now, I'm going to move some things around. I'm going to rewrite these square root of negative 1s. Oop, that pen is dead. I'm going to rewrite these square root of negative 1s as I. We know what that is. And we have 2 of them, so really we have I squared. And then we have that square root of 15, square root of 3. Now we saw this a little bit in the 2.2 homework of kind of dealing with perfect squares and can you factor them out. We had that square root of 28 to deal with on that one. Here we have something similar. I don't see the perfect square yet, but I'm going to throw these back under the same radical to kind of help us out. 15 times 3 is 45, and we have that I squared. 45 now is easier to kind of see what perfect square is in there. 45 is 9 times, right, 5. So we can break this up as 9 times the square root of 5 times I squared. I'm just going to keep the I squared for now so we see what's happening with it. Well, we know this, perfect square, right? Square root of 9 is 3. It's not that we don't know the square root of 5, but it's not going to be a nice exact value, so we're going to leave it as the square root of 5. And then lastly, we're going to finally deal with this I squared. That way we don't lose track of that negative too early on. It's going to be a negative 1, which makes this a negative 3. So whenever we're dealing with any arithmetic with radicals and there's negatives, we want to rely on being able to pull that negative 1 out and treat it as an I, because now we can deal with real and imaginary pieces. Normally I'd have you guys try the next few, but we got some mixed operations, so I'm going to kind of continue working with you guys on these. Next up, number 14, very similar idea. I'm going to kind of skip one step though. I rewrote this as 15 times, square root of 15 times square root of negative 1. We got that from here, right? And then I turned it into an I. I'm going to turn it right into an I right away. So here I have square root of 27i, right? That's where we got the square root of negative 1, minus the square root of 12i. So all I did was kind of skip this middle step and go straight to here. Now, I know it's been a while probably. If you do arithmetic, aka adding, subtracting, multiply, divide, with radicals, multiplication, division, super easy, super sweet, right? We can break it up, move it around, put it back together. When it comes to addition, subtraction, we have to treat it like terms. So we have square root of 27s over here and square root of 12s. They're not like terms yet. But we want to rely on our knowledge of perfect squares and see if we can pull any out. Well, 27, speaking of square root of 9, 27 is just 9 times 3. We can break that up with the radical. So it's square root 9, square root 3i. And I know 12 is 4 and 3, right? So we have square root of 4 times the square root of 3. And again, I. So now we're getting a little bit closer. I know what square root of 9 is, right? Square root of 9 is 3. And I'm going to bring the I with it, just so I don't lose track of the I. So that was handling our square root of 9 and the I. What's left over is that square root of 3. So we have 3i of those square root of 3's. I'm going to do this very similar idea over here. Square root of 4 is 2. I'm going to bring the I over, and I can because it's just multiplication within that little piece. And then we have left over the square root of 3. Now these are, in a way, like terms. We have 3i, that's how many we have, of these square root of 3's, and we're going to remove 2i of them, of these square root of 3's. No different if I had 3x minus 2x. They're like terms. We could subtract them. Well, then how many do we have? We have, well, 1 left over. I square root of 3. So definitely when it comes to adding, subtracting these, a little more extra work we got to do to kind of relate them down to some like terms in order to do anything where for multiplication, division, we're just finding perfect squares. Now, lastly, just for the challenge, I'm going to have you guys give number 15 a chance. Give it a pause. Remember to rewrite this square root of negative 5 as an I in there, and then we'll work it out together in a second. All right, hopefully you tried number 15. It's a fun one. Number 15. So this right here, it's some binomial squared, and we have a process for that, right? First, we square the first piece, negative 2 squared. We're going to multiply these two pieces together and then double it. So 2 times negative 2 square root negative 5. And then after that, we square this last piece. But if you square it in the square root, what happens? Square root goes away. We just get minus 5. Now, if you wrote this again by itself and you FOIL, totally fine. I'm just kind of skipping that step to get to the middle. So now I'm going to do a little simplifying. Negative 2 squared, we get 4. Right here, I'm going to get negative 4. So here's the 2 times negative 2 times the square root of 5. And as I remove the negative from inside the radical, just like I did on the problems before, if I pull out that square root of negative 1, I can make it an I instead. So I can now relate it now to the imaginary numbers, and then I'm still subtracting that 5. Well, last little bit, combining like terms. My real piece is the 4 and the negative 5, which is negative 1. And then, although this isn't really pretty, right, we have no other imaginary pieces, so that negative 4 root 5, that whole thing is our imaginary piece. And sometimes, whether it's the book, myself, in the future, you might see where we put that 4 root 5 in parentheses just to keep a little bit better track of it. So we did a little addition, subtraction, little multiplication, special multiplication with conjugates, and then we can use those conjugates and just the basic definition of I itself being square root of negative 1, in order to simplify a bunch of problems where we're now dealing with negatives in the radical. But now that we can deal with negatives in the radical, that means all those problems of quadratic formula that gave us no solution, we can now look into to see, well, what type of solution does it have? So as we get to the bottom of that last page, ultimately we're being asked to solve a quadratic equation, right? If this was a quadratic function, this would be the same as finding the x-intercepts. So we're going to go ahead and do it. Right off the bat, I'm looking at this leading coefficient as a 7 instead of a 1. That makes it nice for us. And I already don't want to do any guess and check with factoring, so I'm just going to jump straight to quadratic formula, save myself the trouble. So here's our A, here's our B, here's our C. We get negative B plus and minus square root of B squared, there's our 25, minus 4 times A times C. And this whole thing over 2A. Now, like normal, we'd work with simplifying this, right? So we go down, we get negative 5 plus or minus 25 minus 4 times 7, 28, double it, 56. That whole thing over 14. And we keep going, right? That's typically what we do. And some of us are seeing where we already have an issue, maybe. 25 minus 56, we get negative 31. This whole thing over 14. And right, we freak out. We normally go, no, we can't do that, right? Can't be negative. However, we're now welcoming in the idea of complex numbers. So we're allowed to have imaginary values. So let's work at having imaginary values with this. So I'm going to move this over. And I'm going to break this up a little bit. I'm going to get not only the I out of here, right? That's square root of negative 1. But I'm also going to break up the real piece of it and then the complex or the imaginary piece of it. So for the real piece, I got that negative 5 over 14. Similar to how we broke it up on the problems above. And now we have plus and minus. And it's very important we have that plus and minus, right? Square root of 31 over 14 for the imaginary piece. And then I'm missing one detail. Do you notice it? I notice it. Where'd my negative go? Well, square root of negative 1. It's telling me this is a complex piece. So typically we would get to here and go, oh, D and E does not exist, right? But now we're allowed to deal with this. So we're able to get zeros that are going to be complex. Now, this is where we kind of face a little issue of zeros versus x-intercepts. So this part you don't necessarily need for the homework, but it's going to be useful and we'll cover it again coming up. If I have a 0, that's where my function equals 0. But technically, if I have x-intercepts that are complex, they're occurring off the x-axis. And here's the reason why. When we typically graph, we're dealing with the real numbers, where this is the x and this is the y, correct? Well, when we're dealing with complex numbers, this is the real axis, then up here is the imaginary axis. So down the road, we'll do things called polar coordinates and things, and this will make a lot more sense. However, only the real things are showing up here, and the imaginary is going to be floating either up or below that axis. So when it comes to having imaginary zeros, it is not actually crossing the x-axis at that point. Another example of this is when we have a parabola, there were 3 options for a parabola, right? Either it sat right on the x-axis, so it had 1, 0 right there. It crossed the x-axis twice, where we had those weirdos that were that third option, right? They either floated completely above or below an axis, in which case there was no intercept. This was an example of when we had a complex solution to that quadratic function. So that's a way to kind of tie it into parabolas. But there's one last important piece, and you're going to really want to know this now because it's going to save you a ton of trouble, especially when we get to 2.5. Look closely here. What did I say was really important? That plus and minus, right? So although this is a pretty nasty looking imaginary and complex number, I'm going to write it out real fast. 31 over 14i. There's one of our answers, right, when we add it. And then here's the other one. Now, where have we seen something like this before, where it's the exact same, right, but the only difference is one is a positive imaginary piece, one is a negative imaginary piece. These are complex conjugates. So a nice thing to know is if I give you one complex, 0, its conjugate has to come with it. So if I tell you ever that, say, 4i is a factor of something, or a 0, you know so is negative 4i. And this is something that's going to be helping us a ton in the next section. But for now, we're focusing on just our ability to work with